Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalo and I'll be guiding you through the chemistry course. Let's consider quickly energy and chemical reactions. So in this particular lesson, we'll look at what is energy. We'll talk about energy changes in chemical reactions. We'll look at exothermic and endothermic energies reactions. We'll also consider heat of reactions and chemical bonds, and then bond energy, lattice energy, and chemical thermodynamics. All right, let's go into it. So when the word energy is being mentioned, what comes to mind? Well, there's general definition for energy. Popular one says energy is the ability, the capacity, or the potential of doing work, something that is required to get work done. But we also know, according to the law of conservation of mass, conservation of energy rather, that energy can neither be created nor destroyed, but can be transformed from one form of energy to another form of energy, which means one kind of energy disappears and another kind of energy is created. So when you burn let's say magnesium in the presence of air, you have fire, and your fire contains two types of energy, which are heat energy and light energy. You have a bright flame, that's light energy, and you have the heat energy. So you see the potential inside the magnesium is being expanded, is being used, is being consumed, and a new substance is formed. So in like manner, we have different reactions that have different kind of energies involved in them. So let's take a short break, and when we get back, we'll look at exothermic and endothermic reactions. In a few seconds, some questions will be displayed on your screen to test your understanding of what has been taught in this lesson so far. Please do well by answering them. We want to know how much you've understood. Thank you. Welcome back. So earlier we were talking about energy. And we said that in each chemical reaction there is always energy. But how much of energy? That's another question that comes to mind. And one of the reasons why one of the things that gives this explanation can be found in a particular definition of heat content. So about now, the definition of heat content will be displayed on your screen. Heat content, that is the standard heat of reaction of a particular, is the amount of heat evolved or absorbed by a chemical reaction which occurs when a chemical reaction occurs between two molar quantities. So we have very many different units of energy, but basically we work with energy as joules. We work with energy in joules, and in the course of we have to understand that temperature is one of the major aids with which we measure energy. So we define 1 joule as the amount of energy that is used to raise the body temperature, the temperature of 1 gram of water by 0.239 Kelvin. Of course, that's also displayed on your screen. The amount of heat required to raise the body temperature of 1 gram of water by 0.239 Kelvin or degrees Celsius. So that is what 1 joule of energy is. Alright, let's talk about endothermic and exothermic reactions. What do we mean when we say a particular reaction is endothermic? What do we mean when we say a particular reaction is exothermic? You see, when you mix tetraoxosulfate 6 acids, when you mix it with in earlier classes we discussed about reactions of group 1 elements. We say when you drop a group 1 element into water, cold water, they react violently. Of course, this violent reaction is oftentimes accompanied by giving off of heat. So for example, we have sodium reacted with H2O. It gives us sodium hydroxide. Let's have this to let's have this as 4. Let's have this as 4 as well. So I have this as 2 and then plus oxygen gas. So we have sodium hydroxide being produced. Now this particular reaction is accompanied by heat being given off, and when the heat is given off, when a particular reaction gives out heat more than it actually takes in, it is regarded as an exothermic reaction. It is regarded as an exothermic reaction. But in the process of you turning oil, fat into margarine, you have to add heat to the process. In fact, about exo and endothermic reactions. When we say a particular reaction is exothermic, it means that when the components, when the reactants are mixed together, a large amount of energy, usually heat energy, is being given off. It is being given off. That is, the inside environment is hotter than the outside environment, so energy is being given out. While in endothermic reaction, the system is cool. That is, the inside environment is cold and it needs heat energy from the outside environment to occur. Take for example the reaction between sodium and water. We discussed that earlier, that it reacts violently with water. So that's kind of an exothermic reaction. When the reaction occurs, heat is being given off. But in reaction of magnesium with water, of course, we said magnesium only reacts with steam. So we had to apply heat for the reaction to occur. Now, we don't just judge based on amount of energy that is being injected into the system. Rather, we judge based on the comparison of the different of the two energies. That is the difference between the two energies. Now, in exothermic reactions, we have our reactants on high energy and our products on low energy. So energy drops to low. So if it is its content, our energy drops from high to low in exothermic, while in endothermic our energy moves from low to high. We have products at the top and we have reactants at the bottom. So this is what occurs in the reaction of endo and exothermic. That's the exothermic and the endothermic reactions. Okay, let's talk about heat of reaction. Of course, we have just said that heat is usually being involved when a particular reaction occurs. Either it is released to the environment or it is gained by the environment. It's either gained by the environment or it is gained by the system. So what are the different types of heat that are involved in chemical reactions? We have quite a number of them, ranging from heat of reaction to heat of neutralization and all the rest of them. They are all definitions. So on your screen about now, there will be each of those definitions being displayed for a duration of time while I would read it out to you as well. Alright, we have the heat of formation. The heat of formation is the standard heat of formation of a substance is the heat evolved or absorbed, i.e. the enthalpy change, when 1 mole of that substance is formed from the elements under standard conditions. So like ammonia now, when hydrogen and nitrogen react to form 1 molecule, that is heat of formation. Also, the heat of neutralization is the amount of heat evolved when 1 mole of hydrogen ion from an acid reacts with 1 mole of hydroxyl ion from an alkali to form 1 mole of water under standard conditions. We also have the heat of combustion, which is standard heat of combustion of a substance is a heat evolved when 1 mole of a substance is completely burned in oxygen under standard condition. We'll also see heat of solution Standard heat of solution is the amount of heat energy absorbed or evolved when 1 mole of a substance is dissolved in so much water that further dilution results in no traceable heat. And we have also yes, those are the definitions. Those are the definitions that we have under heat of reactions. We have a number of them. They are all talking about the amount of energy, and we are always looking at the standard. And when we look at the standard, we see we are always mentioning standard condition, and usually a standard condition refers to STP, that's standard atmospheric condition, that is standard temperature and pressure. Let's also mention the bond energy. The bond energy is also a definition. We have it there on the screen. The average amount of energy associated with making or breaking 1 mole of a particular bond in a gaseous state is its bond energy. So either the amount of energy that is required to make hydrogen gas or to create steam, each of these things has their bonding energy, but bond energy is associated with gaseous state. While we have the lattice energy, of course displayed on your screen now. Lattice energy is the energy of an ionic crystal. The lattice energy of an ionic crystal is the heat of formation of 1 mole of the ionic compound from widely separated gaseous ions under standard conditions. So you have all these particular definitions. They are all definitions upon definitions. But let's take a more closer look at chemical thermodynamics. So when we talk about chemical thermodynamics, what do we mean? Chemical thermodynamics, we talk about thermodynamics talks about the movement of heat. In chemical thermodynamics, we have a couple of laws. The first law is the first law of thermodynamics. The first law of thermodynamics is also known as the first law. Is also known as the law of conservation of energy. And it states that energy is neither created nor destroyed, but is only transformed or converted from one form to another. So we mean when energy is being moved in particular reaction, when a particular reaction occurs, the energy given off at one particular point is not just given off, it is given off and absorbed at another point. And this is the method in which we use in calculating how much energy has been released by a particular reaction. Peradventure, you have a reaction of sodium chloride, we have sodium hydroxide and tetraoxosulfate 6 acid. We know that tetraoxosulfate 6 acid is quite harsh, and it is very, very used to releasing a large amount of heat. So when we react with sodium hydroxide, we'll have, of course, our sodium salts. That we need 2 molecules of this plus 2 molecules of water, and this will be the output. But this output will not just come out like that. It will come out with a certain amount of heat. Now this heat will immediately be transmitted from the system to the surrounding. So we have an exothermic reaction come into play. Now in some other situations where we do not have the luxury of the reaction to occur, some certain materials, some certain reactions will never occur until you have applied heat, such as the burning of carbon in presence of air. In presence of excess air, we'll have the formation of carbon dioxide gas. Now this particular gas will not be produced unless you have added a lot of heat, and you end up having a hot gas being produced, which is actually lower than the amount of heat. The temperature rather is lower than the amount of temperature which has been injected, or the amount of heat it possesses is lower than the amount of heat which has been injected into the system, to suggest that it is an endothermic reaction. Of course, we have the second law of thermodynamics, which is also being displayed on your screen about now. Second law of thermodynamics emphasizes on entropy and enthalpy. It suggests that the change in entropy is equal to the change in enthalpy divided by the temperature, or change in temperature. This particular expression actually also helps us to understand how certain things occur in the chemical reaction. So what is entropy? Entropy is a level of orderliness or disorderliness of a particular chemical substance. It's level of orderliness or disorderliness of a particular chemical substance at a particular temperature, of course. So we can always identify our enthalpy. We usually represent the enthalpy as TdS, and change in enthalpy as TdS. That is, change in enthalpy, which is change in heat, is equal to temperature multiplied by the change in level and randomness of the substance. Of course, we have talked about kinetic energy before, the kinetic theory, that when heat is supplied to a particular substance, it makes the molecules of the substance move consistently in a random direction, of course on straight lines. So these are the two laws of thermodynamics. They are the two laws of thermodynamics, and they are the ones that we do apply to in chemical thermodynamics. Alright, in this lesson we considered energy and chemical reactions. We started with what is energy. We explained what energy is. We looked at energy changes in reactions. We talked about exothermic reactions, that is reactions that lead to evolvement of heat, and we talked about endothermic reactions, that are reactions that do require heat to be absorbed for them to occur. And we also talked about heats of reactions, the different heats of reactions, where we talked about the heat of solution, the heat of heat of solution, heat of neutralization, heat of formation, and heat of reaction. We also talked about the lattice energy and the bond energy. That's the amount of energy, bond energy, the amount of energy need to break or build a particular bond of a particular gas, and the lattice energy is the amount of heat required to form a particular crystal from the components, which are the atoms, which are sparsely apart. When we looked at the chemical thermodynamics, where we gave the two thermodynamics laws. That's the first law of thermodynamics, which is the same thing as the law of conservation of energy, which states that energy is neither created nor destroyed; it's only being converted from one form to another. And that said, chemical energy can be converted to heat energy. And we also talked about the second law of thermodynamics, where we said that it stipulates that enthalpy equals to temperature multiplied by the entropy of the system. Change in enthalpy equals to temperature multiplied by the change in entropy of the system. Alright, I haven't learned so much about all these things. I haven't discussed these matters. In a few seconds, some questions will be displayed on your screen to test your understanding of what has been taught in this lesson, where you're required to answer them. And if there is any other question that is a little bit challenging, you can go over the video another time to get better clarification. Thank you.